All right, guys, we are on 11.4 Matrix Algebra. So for this section, we have few definitions here that we have to get through before we start the examples. All right. Okie dokie. Two matrices A and B are said to be equal. Written. This feels super fat, doesn't it? There you go. Written. A equals B, provide that A and B, capital means matrix, all right, have the same number of rows and columns. And each entry A sub I j in matrix A, which is now we're using capital letter, is equal to the corresponding B ij in B. Okay, so the lowercase with the subscript, those are each entry, and big capital A and B represents matrix themselves. 2. Sum A plus B. You can only add the matrices if they are the same size. By adding Aij plus Bij, by adding the entries. Now difference is the same thing. We can only add them. Okay, so only if they are the same size, by not adding, obviously, by subtracting the entries, Aij minus Bij. Commutative property of matrix addition. So if we have A plus B, we can compute B plus A. Now, associative property of matrix addition. So we have A plus B first, and then plus C. In addition, that would be the same thing if we were to go and add matrix B and C first and then add A. As you can see, these are not the same for subtraction. Okay, zero matrix. So if we have matrix A plus zero matrix, which is the same thing as zero matrix plus A, which equals just simply matrix A. So the properties for matrix C's addition, they're exactly the same as just the number properties. Property of a scalar multiplication. So we got a few things going on here. So if you have a scalar, let's call it K. A scalar just means any number. And we have another scalar, let's call it H. And we want to multiply it to matrix A. Okay. That should be the same thing as if we were to take two scalars, H and K, multiply it first, and then multiply it to A. Now, property number 2, if we were to do scalar H plus scalar K first and then multiply to A, that is the same thing as if we were to distribute the scalars and then add the matrices. And we have one more. If we have K times matrix A plus matrix B, that would be the same thing as if we were to take the scalar K times matrix A and then add to scalar K times matrix B. Let's pinch that in. 8. Row vector R, okay, is a 1 by n matrix such as this. Here's matrix R. It's a one row, so one row has entry R1, second entry R2 because it's only one row, dot, 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 R sub n. So one row. If you see big capital R, just one row. Now this is kind of similar to column vector C. It's an n by 1 matrix. So if you see a big capital C, it means one column. So entry 1, entry 2, dot, 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 entry however many, okay, one column. The product of R times C, so remember R is one row, C is one column. That means we take your R matrix, okay, and we multiply that to your one column matrix. The result, students, okay, the result is going to be R1 C1 plus R2 C2 dot 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 plus plus here plus Rn plus Cn. I'm out of space. Now this will come up to be just one number. Okay, so the answer, final answer after you add up all of those will give us one number and only one answer. 11. Product of matrix A times B can only be performed, and this is super important, can only be performed if the number of columns in matrix A equals the number of rows in matrix B. All right, so again, that's super important, okay? The number of columns in A must be exactly the same as the number of rows in B. If that's not true, you may not multiply two matrices. 12, associative property of matrix multiplication, which is very similar to addition earlier. So if we multiply matrix A, B first, then C will be the same thing as if we were multiply B, C first, and then times A. Distributive property, if we have matrix A times matrix B plus C first, that's the same thing as if we would distribute and then add. Now, matrix multiplication is not commutative, so that's why we don't have one for multiplication. We just have two more. Identity property. If A is an m by n, so that's row by column matrix, then I subscript m, so identity matrix times some random matrix A will just give us a matrix A, where I matrix subscript m is called the identity matrix. And one more, diagonal entries or the main diagonal. So diagonal entries, or aka the main diagonal for an n by n. So if you have an n by n, now this is a square matrix, okay? So square matrix. The entries located in row I, column I, where your I must be bigger than or equal to 1 and less than or equal to n. Okay, so remember I is your location. Okay, so it's talking about diagonal entries or the main diagonal. It's the right in the middle of the matrix. All right, students. Example 1 from 11.4. Okay, use the following matrices to evaluate the given expression. Now, as you can see, I'm doing a lot in each example. In your book, they may separate these things out. They may just do 2 times matrix A, or they just do A matrix A plus matrix B. No, but if I teach you everything at once, then you can go back and do the easier version of it, okay? So letter A says, I want to have 2, which is your constant or scalar, times matrix A, then 4 times matrix B, and then add it all together. So the first thing we want to start is 2 times A, and then over here, that means 2 times A, and then I need space, so I'm gonna write these out a little bit further apart. So what does 2 times A mean? Well, 2 times the entire matrix. That means the entire, every single entry in the matrix is twice as big. Okay, so 2 times 0 is still 0. 2 times 3 is now 6. 2 times negative 5 is now negative 10. 2 times 1 is now 2. 2 times 2 is now 4. And 2 times 6 is 12. So that's what you do when you multiply a matrix by a scalar. Now, 4 times B is very much the same. 4 times 4 is 16. 4 times 1 is 4. 4 times 0 is 0. 4 times negative 2 is negative 8. 4 times negative 3 is 12. 4 times negative 2 again is negative 8. Then we are going to add these two together. When I add these two together, I'm going to have a 2 rows by 3 columns. Okay, all you're doing when you're adding is you're adding the same location. So 0 plus 16 is 16. Then we're going to take 6 plus 4 is now 10. Then we're going to take negative 10 plus 0 is negative 10. Then we're going to take 2 plus negative 8 is negative 6. We're going to use 4 plus 12. Ooh, that's fat. Okay, let's make it skinnier. Okay. 4 plus 12 is now 16. And the last entry, oops, let's use gray. There you go. Oh, what happened? Okay. The last one is going to be 12 plus negative 8 is now positive 4. So that's a final answer. Let's box it up. And that's how you multiply a scalar, and that's how you add 2 matrices. And again, remember, you can only add 2 matrices if they have the same number of rows and same number of columns. Okay? B. B says, I need to multiply the 2 matrices. Okay? And once I'm done multiplying, I take the answer and I add 5 times this identity matrix. Remember, the identity matrix I subscript 3, that's the size, so 3 by 3. And remember, matrix I, that means there's just ones in the diagonals. Okay, so let's start. I'm going to need a lot of space, so I'm going to box that up so I can organize myself. Okay. First, let's do C times A. So C times A is matrix C, which is this guy over here. I'm just going to copy that down. 4, 1, 6, 2, negative 2, and 3. Times matrix A, which is this guy over here on the left. 0, 3, negative 5, 1, 2, and 6. Okay, that's what it means. Then add 5 times identity matrix of a 3 by 3. Well, 5 is a scalar. Identity matrix, let me give you what it means. Identity matrix of subscript 3 is a 3 by 3 with the ones in the diagonals and 0 everywhere else. That's the identity matrix subscript 3. A 3 in the bottom denotes a size, a 3 by 3. Okay, so if you multiply 5 by the identity matrix, okay, that's what this is right here. Oh, actually, can I just write 5 in the diagonals now, just to save myself some space? Okay, so 5 here, 0, 0, 0, 5, 0, 0, 0, 5. So that's what happens when you multiply 5 to the identity matrix. Next. What's going to take a lot of work would be the C times A, okay? All right, here we go. And I'm going to write everything out very slowly. I would need a ginormous matrix for doing the work of C times A. And so when you multiply matrices, you're going to take row number 1, and then you're going to multiply column number 1 of the second matrix. Okay, so what do I mean by that? So row 1, column 1. So we're going to take 4 times 0 plus 1 times 2. That's what I mean to multiply row 1, column 1. Then same thing, I'm going to take row 1, different color, row 1, column 2. So I'm going to take 4, ready, column 2 is now 3, okay, plus 1 times negative 5. I'm sorry, 1 times, that's row, column 3, 1 times 2. Okay, so you got, this is column number 2. And again, I'm still multiplying to row 1. And the next one is row 1 times column 3. So we're going to take 4 times, so now this is row 1, column 3, times negative 5 plus 1 times 6. Okay, we will work out the basic math later, but I want to write everything out so you are very clear. Next, we are going to try to multiply row 2, column 1. So row 2, column 1. Row 2 is this guy right here, and column 1 is this. So we're going to do 6 times 0 plus 2 times 1. Then we're going to do row 2, column 2, which is this right here, and that. Okay, so 6 times 3 plus 2 times 2. Then we are going to do row 2, column 3. Again, back to row 2. This is my last column. So 6 times negative 5 plus 2 times 6. Okay, so that, we have to do this every time we multiply two matrices. So we're going to do one entry at a time. Then we are going to go back to row 3, column 1. Row 3 is, let me erase a bunch of this stuff because I cover everything up. Okay, row 3 is now this guy, negative 2 times 3, and column 1, oops, what did I say, Dealing? Negative 2, I'm sorry, times 0 plus 3 times 1. Okay, then we are going to be working with row 3, column 2. So again, row 3 is this one, column 2 is back to this one. So negative 2 times 3 plus 3 times positive 2. And the last one, we are going to take again row 3 and column 3. So we're going to do negative 2 times negative 5 plus 3 times 6. Okay, so that's what we do every time we multiply two matrices. Now let's work out the basic math. Are you ready? Okay, so this right here, all of that, it should be a, okay, let me tell you what size you're going to have. Okay, when you multiply a 3, let's talk about the C matrix. Let's pick a color. What have I not used? Did I use? How about green? Okay, so matrix C is, if you look at this right here, 3 rows. Okay, matrix C has 3 rows by 2 columns. Okay, now matrix A has 2 rows by 3 columns. Okay, this is your trick. If these two inner values are the same, that means you are able to multiply. Again, you write down the sides. Okay, if the two inner values are the same, then you can multiply. Now the two outer values, let's pick a highlighter that you can see. The two outer values, like here, that will tell you the sides that your final answer is going to be on. So because it's a 3 and a 3 on the outside, that means your remaining answer will be a 3 by 3 matrix. Oops. Okay, so that's a little secret right there. All right, let's work out the basic math. 4 times 0 plus 1 times 4 times 0 plus 1 times 2. Oh, why 1 times 2? Oops. Sorry, this is supposed to be a 1 times 1. Okay. Oh, that should be, that's confusing to you guys. Okay. sorry, because this is a 1 times 1. So this is row 1, column 1. So 4 times 0, 1 times 1. Ooh, almost missed that one. So 4 times 0 is 0. 1 times 1 is 1. So that's going to be 1. Then 4 times 3, which is 12. 12 plus 2 is going to be 14. So that is 14. 4 times negative 5 is negative 20 plus 6 is now going to be a negative 14. So that's my first row. All right, next is going to be 0 plus 2, so that's 2. 6 times 3 is 18 plus 4, that's going to be 22. 6 times negative 5 is negative 30. Negative 30 plus 2 times 6, that's 12, so that's going to be a negative 18. Next is negative 2 times 0 is 0. 0 plus 3 times 1 is 3. Negative 2 times 3 is negative 6 plus 6 is 0. Then negative 2 times negative 5 is 10. 10 plus 18 is now 28. So that's the product of C times A. Remember, we also have to add 5i. But 5i, we already found the answer. It was 5, 0, 0, 0, 5, 0, 0, 0, 5. My final answer is, because these two are the same, identical in size, I can just add them straight up. Final answer of this entire problem is 1 plus 5 is 6, 14, negative 14 because of those two zeros. Then 2 plus 0 is 2. 22 plus 5 is now 27, and negative 18. 3 plus 0 is 3. 0 plus 0, 0. 28 plus 5 is now 33. So class, your final answer for example B is that. This is example 2 in 11.4. This one says find the product. Remember the previous example, if you remember, we did on B, we did a lot, right? We multiplied two matrices and then we add another one. So if this one is a simpler version of example 1B, it says find the product. That means first I need to check to see if you can multiply these. To check that, you need to find the size of each matrix. The size of the first matrix is a 3 rows by a 2 column. The size of the second matrix is a 2 rows by a 3 column. Remember, I taught you this before if you were listening. If you have the inner values are the same, that means you can multiply, okay? Now the outer values is what the product is going to be. So the final answer would be a 3 by 3, okay? All right, here we go. First, I have to write a big matrix because I want to write down everything for you. So the first one we're going to do is we are going to do this over here, okay? We're going to do row 1. I'm going to write it out. Row 1, column 1. Are you ready? Row 1 is 1 times column 1 is 2 plus negative 1 times 3. That's row 1, column 1. Oh, I might need to expand this a little bit. Then row 1, column 2. So it's going to be 1 times 8 plus negative 1 times 6. Okay, I need to expand this a little bit. And all the way over there. Okay. Then next I need to do row 1, column 3. So 1 times negative 1 plus negative 1 times 0. So the more you do it, the quicker you get. And when you get so good, you don't even have to do this out. You can just do all the basic math in your head. Next, I want to do row 2, column 1. So row 2 is negative 3 times 2 plus negative 1. Row 2, I'm sorry, that means I need to do row 2 is this guy. That means it's 2 times column 1 times 3. Okay? It's easy to make mistake because there's so many numbers, right? Then the next one I want to do is row 2, column 2. So again, this is column 2. So we're going to do negative 3 times 8 plus 2 times 6. And the next one I want to do is row 2, column 3. This is column 3 right here. So we're going to do negative 3 times negative 1 plus 2 times 0. So those are all of the ones that I want to multiply. Now one more. Next, row 3, column 1. row 3, let me erase what I had before. Here's row 3, column 1's that guy. So 0 times 2 plus 5 times 3. And next is going to be row 3, column 2, 4. I know that much. Okay. Row 3 again is 0 times column 2, so that's 8 plus 5 times 6. And we have one more. Let's use green. Row 3, column 3. So 1, 2, plus 1, and 2. So row 3 is going to be 0 times -1 plus 5 times 0. Okay, let's do the basic math, add it all up. So we know that it's going to be a 3 by 3. So now that I can do that, there you go. 1 times 2 is 2. 2 plus -3 is now going to be -1. 1 times 8 minus 6, that's 2. -1 plus any 0 number is now a -1. -6 and a positive 6, so that's 0. -3 times 8 plus 12, so that's going to be a -12. Positive 3 plus 0 is positive 3. 0 plus 15 is 15. 0 plus 30 is 30. And 0 plus 0 is 0. So your final answer is that. And that's how you multiply, baby. Quickly. In Algebra 2, when I said find the answers when you add 3 divided by x plus 4, okay, add 2 divided by x minus 3, what would you get? So find the answer means first, when you're adding fractions, you want to find common denominator. So 2 common denominator, to find the common denominator, you would multiply this side by the other side and vice versa. So this side, I would go and multiply by x minus 3. The other side, I would go and multiply x plus 4. As you now are aware, whatever you multiply to the bottom, you need to multiply to the top. Okay. So this is a 3. This is now x minus 3. Over here, I already had a 2. So now I need to multiply by x plus 4. Now, okay, well, now you have the common denominator. We're going to go a little bit further. On the top, we have 3x minus 9 plus 2x plus 8 all over your common denominator, which is x plus 4 times the quantity of x minus 3. Combine like terms on the top, so that's going to be 5 minus 1. So in Algebra 2, you would say, okay, well, this is my final answer. Oops, 5x. Whoa, almost. Okay. This is x plus 4 minus 3. Now, I'm also going to, some of you, well, can I multiply this out in the bottom? Of course I can. Okay, so if you say, well, that can't really reduce, so I don't need to multiply it out, but some of you love foiling, so you go, I'm going to sit here and FOIL this all out. Yes, I would accept either form. Okay? You can FOIL it out, or you don't have to. Doesn't matter the form that you give me, as long, again, repeating, as long as in the simplest reduced form. Okay? Whenever you're in math class, you got to reduce or simplify your answer. Okay, so that's Algebra 2. Well, partial fraction decomposition, it's the reverse procedure, okay? What do I mean? So let's just read this really quickly. So look, we have the answer we just found, right? This is the answer we found by adding the 2 fractions together. This is what we have here. That's what I typed up. The reverse procedure, starting with the rational expression, and writing is as the sum, or sometimes we subtract, which is the difference, of 2 smaller fractions. So all this is how we're going to go backwards, right? If I give you 5x minus 1 divided by x squared plus x minus 12, now your job is to give me 3 divided by x plus 4, and the other fraction is 2 divided by x minus 3. That's your job for this section, okay? These two are referred to as a partial fraction decomposition. Decomposition. Okay. The 2 simpler fractions, well, This is supposed to be fraction, there's an R in there. The two simple fractions are called partial fractions. Okay, so the reverse process is partial fraction decomposition. Okay, now when you get the two answers, so sometimes 3 or sometimes 4, they're called partial fractions. Okay, now number 2, rational expression is, rational has the word ratio in it, so anytime you hear the word rational ratio is like a fraction, okay, is in the form of P divided by Q, where P and Q are polynomials. And because Q is in the denominator, Q can never ever be 0. Now back in the days, and when you were studying fraction, okay, you also had proper fractions and improper fraction, right? So let me just use a different color. Would you guys remember? This would be like 3/4 would be proper fraction, right? An improper fraction would be 4/3, right? Okay, so same thing here, okay? But we're in polynomial, we talk more about the degree. So in Algebra 2, a proper rational expression is when the degree of P, which is the numerator, is less than the degree of Q, which is the denominator. Okay. Now, improper is when it's bigger than, is when the degree of P is bigger than and equal to, by definition, the degree of Q. Okay, so that's proper and improper. Very similar to basic. When do you study fractions? I don't remember anymore. Okay, there are 4 different cases, and yes, you will have to know all 4 of them for your final exam. Okay, case number 1: decompose P divided by Q, where Q has only non-repeated linear. Remember, Q is in the bottom, and it's non-repeated linear factors. Remember, linear is with the degree of 1. Okay, non-repeating mean that any of the 2 factors cannot be the same. So what do I mean by non-repeating? Under the assumption that Q has only non-repeated linear factors, the polynomial Q has the form. So Q of x is a minus a subscript 1. I'm sorry, ax, because this is a factor, times x minus a subscript 2, and then it can be x minus a subscript n, okay? Where no 2 of the numbers, a1, a2, whatever the a's are equal, okay? None of the a's can be equal. Remember, the factors may not repeat. That means it cannot be the same. In this case, the partial decomposition of P divided by Q is in the form of, ready? P of x divided by Q of x is, okay, A1. That just means any constant, okay? Over x minus your first factor plus some new constant, let's call it A2, divided by x minus the second factor. And you're going to have, can be 2, can be more, okay? Then you can have whatever, how many terms you have, a subscript n divided by x minus a subscript n. Where the numbers, these big a's, a1, a2, an, some books and even later examples, I may use a, b, c. Okay, so it doesn't have to be a subscript 1 or a subscript 2 or a subscript n. It can be a, b, c, d, e, f, okay? Are to be found by you, are to be determined by us. Now, that's case number 1. When the bottom, the linear, the bottom is linear and they cannot be the same. Now, case number 2, where Q has repeated linear factors. I mean, it may have some of the same factors, okay? So if the polynomial Q has a repeated linear factor, Are you ready? Then what happens? Okay, what does that mean by repeating? Okay, this is x minus a. That's a linear. The reason we call it linear because this is a degree of 1. Okay, so that's a linear, and then it repeats. That means it's like to the second power to the third power. Okay, so where this power has to be 2 or more, and n is an integer, then in the partial fraction, here we go. Somehow, mine is on the next page. Okay, decomposition of P divided by Q. We allow for the terms. Are you ready? Here's the formula. A subscript 1 divided by x minus a plus a subscript 2 divided by x minus a squared, and then it keeps on going. Okay, then a subscript n divided by x minus a to the nth power. Okay, so where the numbers a1, a2, an are to be found by us. And again, remember, I don't have to use a1, a2, an. I can use a, b, and c. Okay, these are just anything I want to use. Case number 3. What happened when the bottom is not a linear factor? What happened when it's like a quadratic factor? So if Q contains a non-repeated irreducible quadratic factor of the form ax squared plus bx plus c, then in the partial fraction decomposition of P divided by Q allows for the term. Ready? So for this one, I'm not using a1, a2, but I'm using a and b. Okay, ax plus b divided by ax squared plus bx plus c, where your a and b are to be determined by us. Question number 4. What if you have a repeated quadratic factor? Okay. If the polynomial Q contains a repeated irreducible quadratic factor, such as ax squared plus bx plus c, and then repeating means I can have more than 2 or 2 or more, where n is greater than or equal to 2, and n is an integer. Then in the partial fraction decomposition of P divided by Q allows for the term. Are you guys ready? We are going to start with a subscript 1 x plus b subscript 1 all over your very first quadratic, which is ax squared plus bx plus c. Then I'm going to have a subscript 2x plus b subscript 2 all over ax squared plus bx plus c to the second power. And I can have a lot of terms. We don't know how many terms, depending on how many you can break down. A subscript n times x plus b subscript n divided by ax squared plus bx plus c all to the nth power. Where a, b, okay, a1, b1, a2, b2, an, and bn are all to be found by us. So that's just purely the definition. We are going to look at the next video for the example, but this is the end of our definition. Questions is proper or improper. If proper, rewrite it as the sum of a polynomial and a proper rational expression. Okay. So again, remind you guys that a proper fraction is when the top is smaller than the bottom, and an improper is when the top is bigger. Now in polynomial, we are using degrees. Okay. So example 1, the degree on the top for number a, the degree is the highest power or exponent, so it's going to be 1. The degree on the bottom is 3. So this, as you can see, the top is smaller, so this is definitely proper. If it's proper, you just write proper and you move on. If it's improper, then that's when you have to do a bit more work, okay? So on the top, your degree on the top is going to be 4 because the highest power is 4. The degree on the bottom is 3. So when it's improper, you have to first write the answer. Okay. Then it says if it's improper, rewrite it as the sum of the polynomial and a proper rational expression. This calls for long division. Okay. So how do we do long division? We divide it normally. Okay. So I'm going to do a hockey stick. So if I give you 2475 and I say divided by 5, right? Would you, or let's say 4 because I want a remainder. Then back in the days, you go before calculator, you go 4 goes right here, 2475 goes here, and then you divide it out. Same thing, okay? But inside we have 3x to the 4th. I don't have an x to the 3rd, so fill it in with 0. These are called dummy terms with a 0x to the 3rd. Anytime you have a missing term, you fill it in with 0. Plus 1x squared. I don't have an x, so fill it in with the dummy term, 0x minus 2. Similarly to the bottom. You have an x to the 3rd. I don't have any square term, so fill that in with 0. I don't have any x term, fill in with 0, and then a minus 8. Well, back in the days, how do we divide? We take this and we say, well, 24 divided by 4 is 6. 6 times 24 is 24. Well, and then we go and go, well, I have to change the sign to negative, so we're going to subtract. So that gives me a 0. Then we go further and we drop down to 7. Same exact thing. Are you ready? Over here, I have 4 terms, so I'm going to start with all 4 terms, okay? And so we go, we take this first term and we look at this. We say 3x to the 4th divided by x to the 3rd. That will allow me to write 3x. And we multiply it all back, just like what we did here. So 3x times x to the 3rd is now 3x to the 4th. 3x times 0, or 3x times anything, is now 0x to the 3rd. 0 times anything is 0. 3x times 0x, again, is 0x squared. 3x times a negative 8 is a negative 24x. Now, just like back in the days, we go in and change the signs, right? Whatever sign we had before, we change it up so we can combine them. When we do that, these guys are gone. Now, the zeros and zeros are gone. The x squared minus 0x squared is now I still have an x squared. And 0 and a positive 24 is now positive 24x. And then that's what I have. Now what do you next? You drop down the 5. Same thing. You drop down the negative 2. Well, in this case, when I drop down the negative 2, I can't really divide anymore because this x to the 2nd, what I mean by x to the 2nd is this right here, is not big enough to divide by x to the 3rd. So that is my remainder. So that's what they mean by rewrite it as a polynomial and a proper rational expression. They want you to write it as 3x is your answer, plus, okay, plus we have your remainder, which is x squared plus 24x minus 2 all over x to the 3rd minus 8. So now that's what they mean, okay? Now for you guys, back in the days, can you see that I have the 75 right here? I'm sorry, drop down the 7. I forgot to divide that. So 7 divided by 4 is going to be 1, right? 1 times 4, I'm out of space. So now I have 7. 1 times 4 is 4. You change the signs, that's 3. Now you drop down the 5. So now you have 35. Now 35 divided by 4, not evenly, but I can try, what, 8. 8 times 4 is going to be 32. We go in and we change the sign. Well, as you can see, this is a remainder of 3. So back in the days, we write 3 over 4. But the reason we can just write it next to each other is because technically, this is really 618 plus 3 over 4. But when I do in math, basic math, when you add numbers, plus 3 over 4 is really 618 and 3/4, right? But in polynomial, you can't really do that. So you have to keep this plus sign, okay? All right, and this is the end of example 1.